Hello everyone. We will now begin our lecture on chapter 8.2, which is on polygons. Now polygons are geometric shapes created by connecting three or more lines. So these are shapes with lines and angles, and depending on the number of lines a polygon has, we name the shapes differently. All right, so we will go through all the different types of polygons, starting with triangles, uh, which are figures or shapes with three sides in them. And then we will also discuss how to find their angles and also how we can use them to solve different application problems. All right. So these are the topics that we will cover in this section. First of all, we learn to solve problems involving the sides and angles of polygons. Then we learn to solve problems involving similar figures, and finally we'll solve problems involving congruent figures, and we will discuss the difference between similar figures and congruent figures when we go into that discussion, right? So here we present a definition of polygons. A polygon is a closed figure in a plane determined by three or more straight line segments. And here are some examples of different polygons. This green figure here has four lines connecting, all right, and it's a closed figure. All the lines close upon a certain area. So it's a figure with four lines in them. It's called a quadrilateral. Then here we have this orange figure is an octagon because it has eight sides, eight lines connecting each other. All right, it bounds an area inside. So there are eight lines. It's an octagon. Our stop signs on the road are all octagonal figures. Then we have here another figure. I don't know how to name it, but it has one, two, three, four, five sides. So it looks like it is anything with five sides is really called a pentagon. And then we have a triangle with three sides, right? So when a figure is bounded by three lines, then it is a triangle. We have to know a few terminologies on polygons. The first is that the straight line segments that form the polygon are called its sides, and a point where two sides meet is called a vertex. The plural of a vertex is referred to as vertices. All right, so what this means is, let's take a triangle, which is a polygon. All right, so the straight line segments that form the polygon. So each of these straight lines that meet at a point called vertex. So each of these lines are called sides, and the meeting point between two lines is called a vertex. So a triangle has three sides with three vertices. All right, so the plural of vertex is vertices. And that'll always be the case. The number of vertices will be the same as the number of sides in a polygon. All right, so the next is the union of the sides of a polygon and its interior is called the polygonal region. That means that the area that this figure binds, these three lines, the area that it bounds, including the lines, that region is called the polygonal region. Same with maybe a square. All right, so if we take a square, square is a polygon, all right, with four sides, and this region inside the bounded region uh, by the four sides would be called or referred to as the polygonal region, and that would also include the lines. And then finally, a regular polygon is one whose sides are all the same length and whose interior angles all have the same measure. So a square has all sides of the same length, correct? So a square is a regular polygon. Not only are the sides of the same length, but all the angles, all the four angles formed uh, by the four lines, connecting lines, are also the same. In a square, each angle is 90 degrees. And we can have regular triangles also whose sides have the same measure and whose angles would also have be equal to each other. The angles would be equal to each other. An octagon, the stop sign on the road that we see, that's a regular octagon. All 8 sides are of the same length, and the interior angles also have the same measure. All right. Now, polygons are named according to their number of sides. So, if a polygon has 3 sides, it's called a triangle. We all know that. A 4-sided polygon is a quadrilateral. 5-sided polygon is a pentagon. 6-sided is a hexagon. 7 is heptagon. And then 8 is an octagon. 9 nonagon. 10 is a decagon, 12 is a dodecagon, and 20 is icosagon. All right. So these are the different names given to polygons based on the number of sides they have. Now, every polygon can be bisected or dissected into triangles. There are triangles hidden inside every polygon, and the number of triangles that you can find inside a certain polygon depends on how many sides the polygon has. For example, a 3-sided figure, which is a triangle. So let me draw that figure here. A triangle is a 3-sided figure. It has 3 sides. There's only one triangle, right, in a triangle. Now, for a 4-sided figure, for example, a square or a rectangle, let me draw this 4-sided figure. This can be divided into 2 triangles. All right. So there are 2 triangles in a square. Likewise, in a 5-sided pentagon can be divided into 3 triangles. A 6-sided hexagon can be dissected into 4 triangles. All right. So just look at the pattern. We can perhaps use some deductive reasoning that we learned in chapter 1 on this to figure out how many triangles we can expect from polygons of different sizes. So let's look at the pattern, the way the triangles, number of triangles relate to the number of sides. So when a figure has 3 sides, it has 1 triangle. So what is the difference between 3 and 1? It's whatever 3 is, whatever the number of sides is, minus 3 minus 2 equals 1. Then let's look at the next one. When the number of sides is 4, the number of triangles is 2. For the relation between 4 and 2 would be 4 minus 2, correct? For a 5-sided figure, the number of triangles is 3. So that's 5 minus 2 again. All right, so we are getting closer on the deductive reasoning. Then 6 minus 2 also is a 4, right? So 6 minus 2 equals 4. So if a figure has 7 sides, how many triangles can we expect using deductive reasoning? 7 minus 2 would be 5, correct? If it's 8, then we can create 6 triangles or dissect an octagon into 6 triangles. So the pattern is whatever the number of sides may be, whatever the number of sides is, the number of triangles within the polygon, or that can be obtained from those polygons by dissecting them, is minus 2. 2 less than whatever the number of sides it has. All right. So if a polygon has n sides, then the number of triangles you can expect would be n minus 2. All right, whatever n is, just substitute the number of sides into n and it'll tell you how many triangles you can get out of those, right? Now, the sum of the measures of the interior angles. If it's a three-sided figure, then however many triangles it has multiplied by 180 degrees. So a triangle, the sum of all the angles in a triangle is 180 degrees. All right, so 1 times 180 degrees. If it's a four-sided figure, then the number of triangles within the four-sided figure is 2. So it's 2 times 180 degrees. For five-sided figures, 3 times 180 degrees, 540 degrees. Six-sided, 4 times 180 degrees is 720 degrees. Again, these multiples are the same as the number of triangles. And what was the formula we came up with through deductive reasoning to calculate the number of triangles from the sides? It's n minus 2. So you can get the sum of the measures of the interior angles for any polygon by using the formula n minus 2 times 180 degrees. All right, so we just applied our knowledge of deductive reasoning to come up with a formula to not only determine the number of triangles you can expect in a polygon, but also to figure out the sum of the measures of the angles, all right, of a polygon. So for in a square or a rectangle, which is a figure with four sides, the number of triangles you can expect is 4 minus 2, which is a 2, and the sum of all the angles in a four-sided figure is 2 times 180 degrees, which is 360 degrees, right? Now let's talk about triangles, which are the basic shapes of a polygon. Now I use the word basic because in order for a shape to be a polygon, it has to have a minimum of 3 sides, right? And all the other shapes are formed from triangles, really. All right, so we saw in the previous slide that we can extract triangles from different polygons. So there are two types of triangle. Well, there are actually, we learned there are different types of triangles based on the angles, but two of them are acute triangle and obtuse triangle. Now, we talked about acute angles. Acute angles are angles which are between 0, like greater than 0, but less than 90 degrees, right? So any angle measure which is between 0 and 90 degrees is considered to be an acute angle. So when a triangle has all its angles less than 90 degrees, then it's considered to be an acute angle. Or an acute triangle, really. All right, so all the angles are acute, and therefore the triangle is also called acute. In an obtuse triangle, one of the angles is greater than 90 degrees. That's what makes an angle obtuse. An obtuse angle is an angle measure which is greater than 90 degrees but less than 180 degrees. So in this figure here, one of the angles is an obtuse angle. The other two are acute angles. Now, if one of the angles is an obtuse angle, the other two will always be acute angles. All right. And again, keep in mind the sum of the angles in any triangle, no matter how big it is or what the shape of the triangle is, it'll always add up to 180 degrees, the sum of the angles. Now, the two other types of triangles are the right triangle and the isosceles triangle. The right triangle is one where one of its angles is a right angle. A right angle is a measure of 90 degrees, right? Any angle that measures 90 degrees is called a right angle, and a triangle that has a 90-degree angle is called a right triangle. Now, the isosceles triangle is a triangle that has any two sides equal to each other, and therefore it will also have two angles equal to each other. And conversely, if any triangle has two angles equal to each other, then it'll also have the two sides equal to each other. All right? Then we have the equilateral triangle. That's a triangle where all the three sides are equal to each other, and therefore all three angles are equal to each other. So a triangle has 180 degrees, right? The sum of all the angles, all right, three angles in a triangle equal is three angles in a triangle sums up to 180 degrees, and if all the angles are equal to each other, then you can equally divide 180 degrees by the three angles, and each angle will have a measure of 60 degrees. All right, so in an equilateral triangle, not only are all the sides equal to each other, but each angle measure is 60 degrees. They're all equal to each other. In a scalene triangle, no two sides are equal in length. In fact, none of the sides are equal to each other. Now let's explore the idea of similar figures. So two figures are similar if their corresponding angles have the same measure and the lengths of their corresponding sides are in proportion. So the keywords here are corresponding angles and corresponding sides, and I'm going to explain what corresponding angles and corresponding sides are. So first of all, we see here two triangles. One is a bigger one than the other, but they have to be positioned so that we can visualize that they are similar figures. All right, so that's how they've been positioned. All right, we can tell that they look similar except that one is a miniature size. The second one is a miniature size of the other one, right? So over here, the corresponding angles in this orange triangle B, angle B is equal to angle E in similar figures. All right, so in similar figures, this is what will always happen. Angle B will be equal to angle E. All right, so B and E are corresponding angles. Likewise, angle C will be equal to angle F. They are corresponding angles. Angle C will be equal to angle F, and angle A will be equal to angle D. All right, so given that they are similar figures, so we have to know first of all that they are similar figures. If that is true, then their corresponding angles must be equal to each other or will be equal to each other, and the corresponding sides will be in proportion. Obviously, the sides are of different length, but they will be of a certain proportion. Now, what are the corresponding sides here? Let's use this color. So side BC corresponds to side FE. The side CA, all right, CA corresponds to side FD, and side AB, all right, let's get a different color, AB corresponds to side ED. And the sides will not necessarily be equal, but they will be proportional. Now we can use the properties of similar triangles to solve various kinds of real-life application problems. This is an example of using similar triangles to find the height of a tree. So let's read through it. Monique plans to remove a tree from her backyard. She needs to know the height of the tree. Monique is 6 feet tall and determines that when her shadow is 9 feet long, the shadow of the tree is 45 feet long. How tall is the tree? So we understand that there's a tree and she wants to know the height of the tree, correct? And we are going to use the idea or the properties of similar triangles to solve this, hopefully. Now, this said there's a figure, but it's in the next slide. But let's try to come up with a figure ourselves based on the information in this slide. All right, so first of all, there's a tree and we have to find its height. So I'm going to draw the tree. So let's say this is the tree. Let's draw a tree here. All right, and we have to find the height. This is the information, the question that we have to answer. How tall is the tree from the ground up to its top? All right, so sorry, let me just redraw the top of the tree. So we are trying to find its height. That's what we have been asked to solve. So we'll just label it's X feet tall. All right, we have additional information. Then it says Monique is 6 feet tall and determines that when her shadow is 9 feet long, the shadow of the tree is 45 feet long. So there's Monique, and I'm going to draw Monique now. Let's draw a picture of Monique. All right, and she stands on the ground here, and she is 6 feet tall. So this height, her height, Monique's height from head to toe is how much? 6 feet, right? 6 feet. And then she says that her shadow at a certain point in time is 9 feet long. So her shadow would fall on the ground. So let's mark that black. So I'm going to do the shadow or show the shadow like this, falling on the ground. And that's 9 feet. That's 9 feet long. All right, so this measure is 9 feet. All right, and then the shadow of the tree at that same point in time is 45 feet long. So let's draw the shadow of the tree like this. All right, and that's 45 feet long. 45 feet, sorry, not 4 feet, it's 45 feet. 45 feet. All right, so to find out whether we can apply the properties of triangles, we need to have triangles. So far we have two separate figures with two sides only. All right, from here to here, and let me just extend this all the way up. All right, now if we connect these two ends of each figure, we will get a triangle. All right, or we will get two triangles, so to speak. So I'm going to connect from the top of the tree, all the way to the end of the shadow. All right, all the way to the end of the shadow. Likewise, from Monique's top of her head all the way to the end of her shadow, if I connect that by a straight line, we will get two triangles. All right, two triangles. And just a second. All right, so now that we have two triangles, we have to see if we can come up with the setup of proportions here. So by the property of similar triangles, they say the corresponding sides are proportional. So what would be the corresponding sides of these triangles? The height of the tree and the height of Monique, they correspond to each other. They are proportional. So we can write those two heights as x divided by 6. All right. And then this height or the length of the shadow of the tree and the length of Monique's shadow are proportional. All right. So they are corresponding sides, so they will be proportional. So it'll be 45 over 9. All right. So if you have taken x and put it in the numerator of the tree, then you have to put the 45, which also pertains to the tree, to this triangle on top as well. And in the numerator is what I mean. All right. So it's going to be 45 over 9. All right. It's going to be the length of the shadow of the tree over or divided by the length of the shadow of Monique, right? So now that we have set up the problem in the form of ratios, let's see how to solve it. All right, we just have to solve for x at this point, but let's go to the next slide and see if they have a similar figure. So let's go over the figure that has been provided in the slide. They have drawn the tree all right, and they have indicated its height that we need to find as x. And then the shadow of the tree is 45, right? Now, for the other triangle formed out of Monique and her shadow, the only difference that they have made between the way we worked it is they have put that triangle within the triangle formed by the tree and its shadow. All right, so we had it like this, correct? We had Monique outside the first triangle, the triangle of the tree. All right, but both should give us the same setup and the same answer. It doesn't matter. All right, so we had two separate triangles outside of each other. Here they have the smaller triangle inside of the larger triangle. All right, so let's go into solving this problem. So here they have solved the problem. Let x represent the height of the tree. So the proportion they have set up is height of tree over height of Monique. That's exactly what we did, and which is equal to length of tree's shadow divided by length of Monique's shadow. So we created a ratio with the heights and created another ratio on the other side of the equal sign with the length of the shadows. So x divided by 6 equals 45 divided by 9. That was the exact setup that we had come up with. And now you cross multiply in solving for x in a situation of ratio and proportion. You just cross multiply. X times 9 or 9x is equal to 45 times 6, which is 270. Solve for x by dividing both sides by 9. All right, and you get x equals 30. That means the tree is 30 feet tall. All right. Now let's talk about congruent figures. So in similar figures, we saw that the angles of two triangles are all the same, but the sides are not equal, but they are proportional. The corresponding sides are proportional. In congruent figures, the sides as well as the angles all are equal. All right. So if corresponding sides of two similar figures are the same length, the figures are congruent. So in congruent figures, the corresponding sides as well as the corresponding angles are equal. All right, they have the same measure. So we have covered triangles, which are polygons with three sides. Now we'll talk about four-sided polygons, and Those figures, polygons with four sides, are called quadrilaterals. So quadrilaterals are four-sided polygons, the sum of whose interior angles is 360 degrees. We learned before that the sum of all the angles in a triangle, right, in three-sided figures is 180 degrees, right? The sum of all the angles, if we added up all the angles, then it would give us 180 degrees, no matter what kind of triangle it is, what shape or size of the triangle is, the angles will always add up to 180 degrees. Now for four-sided figures, quadrilaterals, the interior angles will all add up to 360 degrees. Now, quadrilaterals may be classified according to their characteristics. For example, a square is a quadrilateral figure. It has four sides, but the special property of squares is that the sides are all the same, right? The length of the sides are equal to each other, and the angles are all 90-degree angles. All right. Likewise, a rectangular figure is also a four-sided figure. It's a quadrilateral. A parallelogram is a quadrilateral figure, a trapezoid. So these are all different kinds of four-sided quadrilaterals. So here we talk about some of the special quadrilaterals. In a trapezoid, there are two opposite sides that are parallel to each other. So two sides are parallel. You see the top and the bottom sides in this figure, they are parallel, but the other two sides are not parallel, right? In a parallelogram, all four sides, well, the opposite sides are parallel to each other. All right, we cannot have all four sides parallel, but the opposite sides are parallel in a parallelogram. So both pairs of opposite sides are parallel. Both pairs of opposite sides are equal in length. That's important too. All right. Now, two other quadrilaterals are rhombus and rectangle. All right. A rhombus is a figure with both pairs of opposite sides parallel and the four sides are equal in length. So it has the property of a square as far as the length of all the sides are involved. They are all equal in length, the sides, but the angles in a rhombus are not 90-degree angles. All right. That's the property of a square. Here the angles are not 90-degree angles. However, the opposite sides are parallel to each other. For a rectangle, both pairs of opposite sides are parallel. Both pairs of opposite sides are equal in length. The angles are right angles. So what that means is that the angles are all right angles. All right, then this opposite sides are of equal length, and the opposite sides are also parallel. And finally, we have the square, which is a quadrilateral with both pairs of opposite sides parallel. The four sides are all equal in length, and the angles are right angles, 90-degree angles. So let's look at this last example to find the angles of a trapezoid. So in order to find the angles of a trapezoid, we are going to use the properties that we learned on quadrilaterals, on trapezoids, on parallel lines, perhaps as well as angle measures and their relationships. So the question says trapezoid A, B, C, D is shown. So we have a figure here, and then it says determine the measure of the interior angle X, and part B is to determine the measure of the exterior angle X. Exterior angle Y, which is this outside angle. And this figure is a trapezoid with the fact that it's a trapezoid tells us it is the two lines here, AB and DC, are parallels because uh, opposite only two opposite sides are parallel in a trapezoid. Now let's look at the angle measures given to us. We are told angle A is 130 degrees. Angle B, they haven't explicitly given the value, but this notation here of this right angle, all right, of this box at the corner uh, in angle B tells us that this is a 90-degree angle. That's a notation to represent a 90-degree angle. So we can safely assume this is a 90-degree angle, and so is C is also a 90-degree angle. Now that we know that uh, now that we know the measures of three angles, we should be able to find the fourth angle using the property that the sum of all the angles in any quadrilateral figure, any four-sided figure, is 360 degrees, right? So we can write it as angle A plus angle B plus angle C plus angle D is equal to 360 degrees, correct? Now, just substitute the values. Angle A is 130 degrees, angle B is 90 degrees, angle C is 90 degrees, and angle D is X, which is equal to, so the sum of all the four angles is equal to 360 degrees. So let's solve for X at this point. Sum up 130 plus 90, and that should give us 310 degrees plus X equals 360 degrees. So solve for X by subtracting 310 from 360. So 360 minus 310. Therefore, X is a 50-degree angle. We know that. This is a 50-degree angle. So now that we know X, we can easily find Y, because this X plus Y is an angle about a straight line. So X plus Y is equal to 180 degrees, right? That's what we learned previously in the previous section of this chapter in 8.1. So X plus Y equals 180 degrees. X is 50 degrees plus Y is 180 degrees. So solve for Y and we should get 130 degrees for the measure of Y. So 180 degrees minus 50 degrees when we solve for Y should give us 130 degrees. All right, so now we know the measures that we were supposed to find, measures of angle X and Y that we were supposed to find. So let's look at the solutions that were provided here. The same thing, the same as what we did before. They took each of these angles DAB. So DAB is 130 degrees. Measure of angle ABC is 90 degrees. They haven't filled that in. Measure of angle BCD, and finally measure of angle X, which is CDA, is equal to 360 degrees. The sum of all four angles is equal to 360 degrees. They plugged in the different values, and the values of angle ABC, in other words angle B and angle C, are 90 degrees each. So from here on they just solve for X and they got 50 degrees, same as what we got when we worked on it. All right. And to solve for the exterior angle Y, they use the theorem or the property that measure of angle X plus measure of angle Y should add up to 180 degrees. Any angle about the straight line will always be equal to 180 degrees. So they plugged in the value for the given angle or the known angle, which in this case is X. All right, that should have a value of 50 degrees. So y will be 180 minus 50 for a value of 130 degrees, and that's exactly the answer we got as well.